Part B.2, general solution of binary bits problem. Now, we guessed the general formula from B.1, but we do not know if our guess is correct or not. So in this video, we want to show it is correct. All right. So let's look at what strategy we should take to show it, here, to show the result is correct. Yeah. Here, the strategy, we like to use one that we used before. Yeah. So that is guess and verify approach. Yeah. In problem solving, this strategy is used quite often. Guess and prove or verify. Yeah. Because let me give you the general reason we use this strategy. When we solve some relatively hard problems, usually we do not know what is the answer, right? If you do not know the answer, you may not have good direction to go. You do not know where to start, what tool to use, a lot of things unknown. So in that situation, in order to have some good direction, so usually people guess, if you can pretty much guess a relatively close result, then you have a better chance. Because you should go that way. Although you may have some small error, sometimes you can make adjustment easily. The better the guess you can make, the easier you can solve that problem. So that is the general rule. All right, so here actually we have a pretty good guess. Yeah, because our guess, it's not coming from nowhere, right? It comes from some reasonable work. Yeah, it comes from our work, and from there we make a reasonable guess. So that's what I want to convey. Yeah. All right. So this is the formula we guess. Yeah. Why we can guess such a precise formula? Why we can make that guess? Because we look at a special case where n equals power of 2. In that form, it is pretty easy to find the solution, and that special case solution, we feel for the general case, it should be pretty close to that. Okay, yeah. Then we make this guess. All right, next, let us do the proof. Yeah, but how do we prove it? We need something special. We need a special tool to do it, a powerful mathematical tool. So what's that? You learned that before in your discrete math course, Math 3000, discrete math. Do you still remember there is a method called mathematical induction? That is a very powerful tool. So we need to use that here. Yeah. All right. I hope you still remember the basic steps using mathematical induction. Here, let me just apply it directly. Hopefully, you can recall a little bit how to use the mathematical induction. There are 3 steps. The first step, we need to check the base case. We need to start from somewhere. So usually, we should have some simple base case. Here, our base case A of 1 equals 1, right? We know A of 1, we, using that 1, the meaning, A function meaning, A of 1, because A of number of addition, right? Here, we need to make that A of 1 equals 1, because you may argue Y of 1 is 1, right? Someone may argue Y of 1 is 1, because we define A1 the number of addition. So we can make a special treatment. A of 1 comes from 0 plus 1. How about that? Although it's a redundant addition, 0 plus 1, redundant addition, but in order to make the formula look good, so let us make that. All right, A of 1 equals 1. That 1, then we verify this formula, plugging 1 at the right-hand side, 1 plus log base 2 of 1. Log base 2 of 1 equals 0, flow function also 0. 1 plus 0, both sides equal to 0, equal to 1. Correct. So we verify. Step 1, we verify. Step 2, induction assumption. We just make assumption, induction assumption. Okay? We do not need to prove anything, just to make induction assumption. What's that? Usually there is a standard way. You should be very careful. Write your induction assumption. All right, here, let's write in this way. We assume A of k equals 1 plus flow function of log base 2 of k. You need to specify the range. Here, the range important. The range for the variable k. All right, so here, when k between 1 and n inclusive, then we assume this equality is correct. That's assumption. Okay, that's assumption. All right, then step 3, the most important step, the hardest step. Okay, the hardest step. Step 3, when when k equals n plus 1, n plus 1, the largest number n, in the range, which one is the largest one? N is the largest. And that largest one plus one more, okay? N plus 1. When k equals n plus 1, we want to verify our guess is still correct. Then we complete the proof. All right, so that's the mathematical induction. Now, let us verify this. We want to show it. Okay? We want to really prove it is correct. This step, we cannot assume it, right? We need to prove it. Not like step 2, we just assume it is correct. Step 3, we really need to prove it. But you can use your step 2 assumption. All right. So let us do the work. All right. Proof, we consider 2 cases. N is odd and N is even. These 2 cases. First, when N is odd, we write N equals 2s minus 1. We know odd number, we can use 2s plus 1 or minus 1. Here we feel minus 1 is a little better than plus 1. Okay? Why? You can see it quickly. Because here we try to calculate n plus 1. But here you have minus 1 plus 1 cancellation. 1 is gone, right? Very convenient. We like to cancel out some number. So for that reason, we assume n equals 2s minus 1. For s greater or equal to 1. The smallest n is 1. All right? Next, left-hand side. We want to show the left-hand side and the right-hand side the same in our guess. Oh, in our, here we yeah, although it comes from the guess, but we say our target. Now, this is our target. All right. Yeah, our target. All right. Compare left-hand side, right-hand side. Yeah. All right. We start with left-hand side first. A of m plus 1 equals A of 2s. Yeah. 2s minus 1 plus 1. Minus 1 plus 1 cancel out. So A of 2s. Pretty neat. Why pretty neat? Because we know, remember the recurrence relation, right? A of 2s equals A of 2s over 2 floor function, right? 2s over 2, that's s. Floor function also s. So plus 1. How about that? Very simple, right? All right. So equals A of s plus 1. Then A of s, we can get the expression from step 2, induction assumption. Why? Because s is in the range. We can check s is in the range. We can easily check it. All right. So we can use the formula from step 2, replace k by s. Yeah. Plus 1, 2, plus 2. Yeah. Yeah. Because you have plus 1 here, you have another plus 1 here, so you plus 2. Yeah. But one step you need to check, s is in the range, because we can get s equals m plus 1 over 2, and we know this expression should be less than or equal to n, and greater or equal to 1, for sure. Yeah, in the range. That means we can use the induction assumption. All right, that's the left-hand side. Okay, yeah, let us leave there. Right-hand side, yeah. Right-hand side, we start from this expression, right-hand side, then replace m by 2s minus 1. Yeah, so we get this. All right. Then log base 2 of 2s. Do you still remember a formula? Yeah, here, let me write it. Log base a x times y equals log base a x plus log base a y. Do you still remember that property? Here we use that. Yeah. When we use that, 1 plus log base 2 of s. Yeah. Because this 1 comes from log base 2 of 2. 2, same. Base number, log base, right? And the, function variable part, they are the same. So it is 1. All right, it is 1. No. Yeah, so we have that. Then at this step, we need to use a simple formula from our textbook. Here, let me give it. Floor function x plus m, any x number, real x number, yeah, plus n should be integer. Yeah. Then when we calculate that, we can pull the integer n out of the floor function brackets. Pull out of the floor function brackets. Now, that's the property. I'll give you the reference location. Yeah, in Appendix A. You can find it. Yeah. It's very easy to see this formula. Yeah. Then we apply it, so this one integer can be pulled out of the floor function bracket. So we have floor function of log base 2 of s plus 2. Yeah. Then we can compare both sides, left-hand side and right-hand side. They are the same. So we verified for case 1, when n is odd, it is correct. Our target equality is correct. Next, case 2, when n is even. Then we need to verify another time. Yeah, then we complete. Yeah. But we need to compare left-hand side, right-hand side expression. And in this case, a little harder than our case 1. Yeah. So let us work on it. Yeah. N equals 2s, s greater or equal to 1. Yeah. Left-hand side, a of 2s plus 1 by the recurrence relation, floor function, so a of s plus 1. Okay? By induction assumption, we have this. All right? And why we can use induction assumption? Because s falls into the range we need, right? Falls into the range in our induction assumption. Yeah. So we have it. Yeah. That's the left-hand side. Okay? Yeah. It looks pretty easy, right? Yeah. But the right-hand side, much harder. We need to do quite some calculation. Yeah, right-hand side. All right, well, we start here, then we need to simplify this expression. But the question here, it is not easy to simplify it. Yeah. So we need a special formula here. We need a special formula here. Yeah. All right, so what's the special formula? This one. This one, okay? Left-hand side seeding function, log base 2 of parentheses n plus 1 equals floor function right-hand side, log base 2 of n, then plus 1. It's not easy to prove. You need to do a lot of work, but here we do not need to prove it. We just use it. And we can find it in Appendix A. Yeah, so let us use it directly. Yeah. All right. Now, because we need to simplify that expression. When we simplify it, because here it's the floor function, right? It's the floor function. So we should use the floor function like this. N equals 2s plus 1. All right? Yeah, n equals 2s plus 1. This plus 1, we can move to the left-hand side. It becomes minus 1, right? So then the seeding function, 2s plus 1, so you get 2s plus 2, right? I hope you can get it. Yeah. I did some manipulation. I hope you can follow. All right? You can follow. All right? We use this formula. Yeah. All right. Then 2s plus 2, is it 2 times s plus 1? Right? The product, we can use the property I gave you in the previous slide. Yeah, so we can use that. Yeah, because we can write, yeah, here, 1 plus log base 2 of s plus 1 minus 1. All right? Yeah, yeah, because 2 times s, so that's the sum of 2 log base 2 number. Then for seeding function integer, we can pull out of the seeding function bracket, right? Similar to floor function bracket. Yeah, we also have that formula. Yeah, we also have that formula. All right. Yeah. So then after we pull it out, plus 1, minus 1 cancel out. So we have that expression. We have that expression. All right. Yeah. Then that expression, look at the left-hand side of this formula. Can we simplify another step, right? This time, n equals s. So we get this, another simplification, all right? Then the original right-hand side, here, the original right-hand side should be floor function of log base 2 of s plus 2. Yeah. Add 1 more to it, right? Add 1 more to it, plus 2. After that, you compare left-hand side right hand side, are they the same? Yes, they are the same. Then we conclude for case 2, it is also correct. So both cases, our statement, our target is correct. So we complete the proof. A little hard, yeah, probably a little hard for you. Yeah. Here you need to use several formulas, but the most important formula, the most difficult formula is this one. The most difficult one, this one. All right? All right. Now, we complete our B.2 video here.